So today is 14, okay. Okay, so if you can see the screen, could you please take attendance? Thank you. Okay, so we have 23 participants at the moment. Okay, we are still waiting just for a while. Okay. Can't hear me. Okay, fine. Okay, so can you hear me now? Sorry, I'm not aware that you can't see. So I hope that you can hear me now. Is it? Can you hear me now already? Okay, fine. I think because of some problem, technical issue. Okay, I have to switch on my Bluetooth. Just. Okay, now everyone can hear me. So this is again your attendance sheets. It takes some time to attend the attendance sheets. So we have 24 participants, not 38. Okay, so 25 persons. So suppose everyone is almost there, so we are not going to wait further, even though there are some people missing. Okay, so I hope that everyone can hear me now. Okay, so if there's no response from anyone, then we'll continue our lecture for today. So today the lecture will be on this. So let me go back to the again, we are here, lecture notes. So now in case there's any problem, could you please either chat to me or just switch on your mic so that I can hear from you. Okay, so anyone who has any problem, just switch on your mic, then we can talk online as well. Okay. So we are going to go to this. We go to the e-Moodle. You can see on my screen, part 6. This is the part 6, so you just click on this, then this is the lecture notes that we are going to talk about. We are going to discuss on the solving of the simultaneous equations that is slightly corrected based on the previous lecture notes. So the previous lecture notes that I put up last 2 weeks ago was having some problem with explanation. So we are going to talk about this in more detail today. Okay. Right. Now our purpose here today is to talk about how to solve simultaneous equations. There are two equations, for example. Let's look at the screen. So you can see that. Let's just try to see, try to understand the problem. Now the problem here is that we have two simultaneous equations. Sorry, any questions? Okay, so someone switch on his microphone, so I have to switch it off. Okay, so there are two equations here. X so there's some problem with the students on the screen asking some questions. Graphic lag. Okay, now if you have the problem with your graphic lag, maybe you can just listen to my voice. I think it will get fixed. I think the problem with the graphic fix is the slowness in there's a problem in the internet line. Maybe there are two versions of this lecture that you can follow. Either you follow the real-time version that we are doing it now, or later on I'll upload this recorded screen onto YouTube, then you can follow it later. Okay. Now I'm trying to fix up some problem. I think there's some problem with some of the students. Okay, let's come back again. I'm sorry to get you delayed. Now let's come back to this. Now say you have two equations, x0 cos x1 equals to 4, x0 x1 minus x1 equals to 5, and you want to find out what is the solution for this set of equations. Okay, so this is what we call a set of simultaneous equations. So today we are going to learn how to do this. Okay, so you refer to this part of the lecture online. I'm going to use my own version. Okay, so this is my own version of equations that I'm going to work on it. So you can try to follow along. Now, how do you find out how the solution is? Now, to obtain the solution for these equations, we are going to use the SciSpi optimized fsolve. So fsolve, as we have discussed in the last lecture, is used for solving optimization problem. So in a sense, the solution to these two equations is a optimization problem. Now, what do you mean by optimization problem? The optimization problem is like this. We do not know what is the exact value of x0 or x1. But if you have found the exact solution for x0 and x1, then this equation will be satisfied. So is the second equation will be satisfied. Right? So you try to search around for the values of x0 and x1. And you adjust x0 and you adjust the values of x1. You adjust it such that the error in the process become 0. Now when you can find out what is the values of x0 and x1 where the error is 0, that means you have solved the problem. Now to make my explanation more specific, let us try to form an equation, say f1 and also f2. Right, so you can form x1, a function of two variables, x0 and x1. So you can try to form one equation f1 to represent this to the first equations, and then you define f2 to define this equation x 0. Now it's very easy. So if you take the right hand side of 4 to the left, then you got x 0 cos 1 minus 4, and you call this a function of f1. And whereas for the second equations, you form another function called f2. And you realize that in this sense, f1 is a function of two variables based on the values of x0 and x1. And this is also functions of x0 and x1. Okay, so if you somehow are able to find out the solutions, say the solution is x0r, x1r, right? So you try to search for what x0 is and what x1 is. Now, if the solution is found, what happens is that if you have found the values of x0 and x1, if you have found the right solution, then when you put in the values of x0r and x1r into the function f1 and f2, then f1 will become 0, and f2 will also become 0. Okay, so the idea is quite simple. So if the values of x0 and x1 is different from the true solutions, then the function f1 will be not 0. Okay, is there some problem with the students? Graphic lag, same. Okay. So the pictures, I mean the video is slow, is it? Anyone else is suffering a serious problem in the video? Okay, now again I suggest that you carry on with the lecture. As long as you can listen to me, that will be fine. You try to follow as much as you can, and later on you can refer back to the YouTube version. Okay, so this video will be recorded and will be uploaded to the YouTube. Okay, now for anyone who is there, could you please switch off? Now for anyone who is there, could you please switch off your mic? Right, you need to switch off your mic, or else you cause a lot of problems. Okay, thanks for switching off your mic. Okay, so to proceed with the solutions, I'll try to construct the functions f1 and f2. So our idea is to provide the functions and then try to minimize the error of the functions. So the way how we do it is like this. So first of all, we have to define a function. Okay, we have to define the function called, say, f1, and this f1 admits two values. It will admit the value of x. Well, you have to supply the values of x into the function x1, but be reminded that the argument that is supplied to the function f1 is an array. Okay, so we are trying to solve a two-dimensional problem. Here you have x0 and x1 as two variables. So these variables have to be supplied into it, and we call the x1 okay, so we call the variable x0 as the first element in x. Then we said x1 is the second element in x. Okay, so what is the f1? F1, according to our definitions, is a function which is this, okay, which is x0 cos 1 minus 4. Okay, so I'm going to define my x0. Well, let me copy this. It will be easier for me to just copy this. X0 like this. So I'm going to define the function here. Return x0 multiply with cos of x1 minus 4. Okay, so in order to use the function of cos, I have to import num_p as np, right? So that the cos is np. So this f1 is a function of x, where x has to be an array that comprises of the first element and the second element. Okay, so let me try to print out the values of f1. So print out values of f1. So f1 is a function that reads in x. Okay, so what is x? X has to be a array, right? It is an array containing two numbers. The first number is x0 and the second number is x1. So let me call the first number is a 1.1 and the second number is 1.2. So this is the function of, this is an array. It is the values of x0 located in the first element 1.1, whereas 1.2 is x1, right? So we are looking at the functions of two variables x0 and x1, and by doing that I'll be able to print out the values of x. Okay, like this. So this is the value, which is the values of f1. The values of f1 when x dot is 1.1 and when x naught is 1.1, when x1 is 1.2. And that is how I define my function of two variables. So likewise, I will also define my function of f2. This is a function of f2, which is x naught x1 minus x1 minus 5. So let me define this. This should be x1 x0 times x1, x0 times x1 minus x1 minus x1 minus 5. So let me check if this is correct. Okay, so f2 is x0 x1 x0 times x1 minus x1 minus 5. So that is the function of f2. So let me print out the value of f2. So the function of f2 when x0 and x1 are taking values of 1.1 and 1.2 is minus 4.8. So that's how I define the function of two variables. Okay, so let me try to define then the functions f. So this is a function of f. So the function of f is a function that would take in f1. Well, it's a function that when it brings in x0 and x1, it will return f1 and f2. Okay, so let me define the function of f. Now this function f is like this. It is equals to the values of the function f1 at x and also the values of the function of x2 and xx. So this is the definition of function f. It is made up of the function of f1 and f2. So when I print out the values of f like this, you can see on my screen. When I do this, the output would be two values. One value is coming from f1, another value is coming from f2. So let me press the button. Right. So this is the values of f1 that come from here. This minus 4.88 is a function of f2. Okay. Now, again, someone who are there, could you please kindly switch off your mic? Now, if you don't switch off your mic, then you are causing some noise to the lecture. Okay, thank you for your cooperations. Okay, right. I'm going to continue. So now what we want is that we want to provide an initial guess to the x, so that the function f would give me the values of 0. Let me say it again. This is an optimization problem, right? So if the x1 and x0 is the root function, is the root value, that means f1 will be 0. It would mean that f1 and f2 will be 0 if x0 and x1 has been found. So our purpose is to provide an initial values of x, so that the Python code allows us to find out what the solution is. So this x is an initial guess. So in order to obtain the root or the solution, we just have to use fsolve. Now fsolve, as we have discussed in previous exercise, is actually a package from SciSpy, right? Import SciSpy, and then we have to import from SciSpy we have to import optimize. Okay, so if I'm not mistaken, then that should be the way. So I suppose that the fsolve is inside this optimize. So let me try to see if I can call out the fsolve. Now fsolve is the command that is being is inside the optimize package in the SciSpy. So to use it, what you need to do is that you have to supply the function you need to optimize. So in our case, the function we need to optimize is f. Now what do you mean by this f? This f is this function. We want to make this f to be 0. Right? That's why we say we want to minimize it. But optimization could mean minimization, could mean maximization as well. So here we want to minimize f by varying x, the variables. So there are two variables here that needs to be varied. So the hope is that when the x, that is x0 and x1, is varied, then f will become 0. So what is the values of x0 and x1 that could make f to become 0? So you just provide the function you want to minimize and the initial guess. So here x here is the initial guess. So to make this to be different from the other, I call this x init. Okay, initial guess ig. Okay, this is the f of ig. Okay, so by doing that, if the fsolve can be called, it will try to read in the values of the initial guess fig, which is 1.1 and 1.2 here, and then put it into the function f. Then the values of f1 and f2 will be evaluated and be returned. And when this fig is when x is fed into the fsolve, it will be passed to this x, right? So this x is actually initially 1.1 and 1.2. So the first element in x will be called x1, and the second element in x will be called x1. So we define this x0 and x1 here, and then we calculate the values of this. Okay. So let's see if it works. It might not be working. Yeah, it seems to be working. So no, it's not working because fsolve is not successfully called. So I think I have to import optimize.fsolve like this. Okay, so fsolve optimize. Okay, let me see what should be the correct. So it should be from SciSpy optimize import fsolve. So that is the correct way to import the fsolve. So we need to import as SciPy. Then after SciPy is imported, then we have to import the fsolve from SciSpy.optimize. Okay, so these are simple stuff. If it doesn't call out, if a package doesn't call out, you just have to do some trial and error to call it out successfully. So I'll call this as I'll call this as solution. Okay, then if the solution is found, then it will print it out. Yeah, so I'll try to print out SOL and see if I got it. Right. So yes, so this is the solution. Now what is this solution? This solution actually is the values of x0 and x1. So we try out the initial guess to be 1.1 and 1.2. Then the fsolve will try to find out from this initial guess the correct values of x0 and x1, so that f become 0. Okay, so I'll call this say x0 solution. x0r stands for roots, is the first element in x, and as a solution I'll put this x1r, the second root, is the second element in the SOL. Okay, so after you have done that, you can actually try to print out f1. So you try to print out f1 and x0r and x1r, right? x1r. You can also try to print out this value. Wait, so you can print out the values of f1 at the root of f0r and f1r. You can also try to print out f2 evaluated at the root. Now what do you expect? That is when you print out, what you get? Wait, I'm updating people from the waiting room. Okay. So if you have found the roots, then what you expect for the values of f2 and f1? So obviously, if you have found the roots, then that means f1, yeah, will be 0, and f2 will also be 0. So I expect that when I press the button, I will see these to print out 0 and 0, or very close to 0. What happened? Functions print f1, f2, f1, yeah. So now there's a problem of the typo error. In order to evaluate the values of f1 and f2 at the functions, at the values of x0 and x1, I have to be very careful. See, when you want to print out the values of the function, you should place it in the argument. Right? The argument of the function should be in a in a bracket, so it should not be in the square bracket. So I always make confusions between the square bracket and the curly bracket. The reason is, okay, so the reason is because in Mathematica we always use a square bracket, but in Python we use this bracket more often. So again, the x1, again, if you look at these functions, it takes on only a x, but this x is an array. So when you want to specify the values of the function, say f1 or f2, you have to only supply the values of x in a single. So this should not contain two numbers, it should only contain one number. Well, I mean the number is that you should define this to be a single variable. So the single variable I'll call xr. So this xr should be an array. So the array should be x0r and x1 are. So if you want to print out the values of f1 at the root, this is the correct way. Okay, so you only supply xr, but you can't supply this exactly. Maybe you can't into the xr here. So this is how you do it, right? So that's how you get the answer. But if you want to skip this part, this is also what you can do. You can also try to just inside the argument of this square bracket, just specify this. I think this should also work as well. Okay, so yeah, it works as well. Okay. So this is how you evaluate the f function, f1 function, f2 function at the values of the root. So this has found, right? So the answer is that in order to fulfill this simultaneous equation, what is the values of x0 and x1? So this is how you construct the code. So you define function f1 and f2, where the argument that goes into this function is actually an array. The array should comprise of the 0th element and the first element. Right? So this should be considered as x0. This should be considered as x1. Right? So once this x is passed into this function f1, then you have to extract the first element and the second element from the x array. Right? Then this is the definition of f1 based on x0 and x1, and so is the way how you define f2 as well. So our purpose is to provide an initial guess to the x0 and x1 so that this f could be minimized to 0. So to do that, you just have to use fsolve, supply the function to minimize, and then you provide the initial guess. Then the solution is found. Once it is obtained, then you can try to put in the solutions. Now it's always very important you use the some functions in the Python. So in this example, the function you use is fsolve. So the fsolve gives you a solution. You cannot just take the solution as it is. You have to check whether the solution is correct or not. So the solution that you obtain is x0r according to my definition here. So I keep the solutions to be SOL. Then I extract the first component and the second component of SOL. After that, then I put these solutions into the argument of f1 and put the solution into the argument of f2. My purpose is to make sure that when these two functions are evaluated at their solution, you indeed get a values which is close to 0. So this is an example of using fsolve to solve a set of set of simultaneous equations. Okay. Now, is everyone okay? Hopefully. Now, any questions from there? I'll wait for your questions. Anyone who want to ask anything can ask now, or I'll just wait, or just send me a message. No? Okay, so the next thing we want, so all the working to solve a two simultaneous equation with two variables is all displayed. Okay, so you can just follow and then try to do this. Now then another example is this. Let's try to solve a function of ex equals to log y, log x equals to e power minus y. Okay, so again, this is a simultaneous equation that has two variables, which is x is the first variable, y is the second variable. So so you have two equations and two variables. Now this is a set of simultaneous equation which is slightly more complicated. We call this a nonlinear equations. Nonlinear in the sense that it's not polynomial. Okay. So what is the values of of x and y such that this equation is fulfilled and this equation is also fulfilled? So we will just do the same thing again. Let me just cut and paste this first, and then we will try to go through how we do that. Okay, it should be very fast. So again, you import SciPy and you import NumPy, okay, because we need to use the log and the exponential function from SciPy and NumPy. So again, I'm going to form one equation that describes this. Okay, I'll call f1 equals to e power x minus log y, and I'll call f2 to be log of x equals to e power y. Okay, so I'll call definition of f1. It should be a function that admits one variable x, where this variable x is again a two-dimensional array. Okay, so this f1 is defined to be exponential. Now, how do you do exponential in Python? It should be np.exp. Okay, this is how you define exponential. So this should be exponential of exp x minus log np.log of y. But we have to be very careful. Here, this x is the argument that goes into a function fy. So this x should contain two components. Okay, and this function here, what goes into the exponent is the first component, what goes into this y is the second component. So you have to be a bit careful. So maybe I'll just call this xarr. So that would make it explicitly clear that what goes into the f1 is a variable which is itself an array. An array comprised of two variables. The first variable in I think okay, thanks for Nurul Akila. Okay, so there will be no on the spot assignment. So there will be no on the spot assignment during the lecture. I think I have some problem as well. The line in many places are slow. Okay, but you can always again try to follow as close as possible. But then if you cannot follow, then you go and revise the YouTube channel. Okay, in the YouTube channel you can just drag along if you don't like my lecture. Okay, you can just go through very fast. Okay, there will be no on the spot assignment. Okay, I will show you that. Okay, so let me come back again. Now this ARR is an argument that goes into the function, and this ARR means what goes into the function f1 is an array. So the first element x is the array, is the first element of the array, whereas y is the second argument in the array. Okay, so that is how we define x and y. Now be careful, the x here and the y here that you see in the definition of the function f1 is what we call a local variable. Local variable means that if you print out x and y outside this definition, the values of x and y will not be passed out. Okay, so let me try to explain what I mean by that. So you can try to print out, say, the values of f1, which is a function. So f1 with a function, curly bracket. So what goes into the argument of the function should be going into the this bracket. So in this bracket I have to supply xarr. So let me call xarr is say 1.1 and 1.2 again. So I call this is the values of 1.2 and 1.r. So this should be actually the values of ARR. So explicitly I can say xarr to be just like this. Okay, it's possible to do that. Then in that case, then I'll just say this as xarr. Okay, so if I don't want to do that, then I can just say this is just the values of f1 evaluated at this. Okay, so I print out and see whether I got anything. So that means yes, so this is the number that is printed out from this return line. Okay, so x in this case is 1.1, whereas y in this case is 1.2. So if you try to print out values of x, what do you think? Do you think you get any number? The answer is, I think you can't. Right? X that goes into here does not appear, and then this one doesn't appear. The y would not be get printed out, even though you think that the y has been defined inside these functions. Okay. So the values of y that is defined here inside the definition of this function is a local variable. So the x is a local variable, y is local variable. The values of x and y defined inside f1 stay in the function f1. Outside the function of f1, like here, if you try to print out the values of y, which is not within the package, well, within the this function f1, will not be possible. Okay, so see, I try to print out y1, no, it doesn't give me, it only gives me this value. Okay, so try to understand the idea of local variables. X or y that's being calculated here would not be passed outside this function. This is what I try to tell you. Okay, so now I have finished defining my function f1. Then I'll define my function f2. Function f2 again is should be log of x minus e power minus y. Okay, so again this will be passed into f2. Then the first element in xarr will be called x, and the next element in xarr will be called y. Right. So I'm going to define my function to be log x minus ey. So it should be log x minus ey, exp. Okay, but it's not y though, it's minus y. Okay, be careful. So this is minus y. So that would define my x, y1 and y2. Okay, so now I will define my function f. Again, it will admit the same variables of xarr, and then it will return two functions, f1 with xarr, and then f2 of xarr. Okay, so now you would sometimes be confused. Why should we define this? Now we define this f in terms of 2 because what we want is not only to minimize f1 but also f2. So to minimize f1 and f2 simultaneously, we define this function f, and then this function is a two-dimensional function that is to be minimized. Okay, so then we call this f soft. Then you just define the function you want to minimize, which is f. Right? So you put f1, f2 in the f. Then you provide an x initial guess. So xarr initial guess. Right? So just provide some initial guess. Now you don't know what it is, but just provide some guess. And then this is xarr that should go into the initial guess. So we are looking at this function of e and y, and you must look at this. You must provide some sizable values. What do you think x is, y is? Now you cannot say x is minus 1, y is minus 1. Y cannot be minus 1 because log of minus number, log of a negative number cannot be defined. Right? So is you cannot say x should be say minus 1 because the log of minus 1. So to provide a reasonable initial guess is one of your homework. So what do you want? Say maybe you put in 1, 1. So let's see if it works. So your initial guess could be 1, 1. Now if you put negative 1 and negative 1, then you run into trouble. Right? So it gives you this sort of warning, and you got error messages. Well, not quite error messages. The answer is 1, minus 1, minus 1. So you put in minus 1, minus 1. The solution is also minus 1, minus 1. It means that whatever you put in is whatever you get from outside, and it looks like there is an error here. Right? So you have to try another initial guess, maybe minus 1, 1. Now again, it cannot be allowed, as I mentioned. The initial guess for x and y cannot be negative because you involve an x and y. Okay, so just check. Let's just try to put it as 1, 1. yes, you get some number. So it looks like the solution for x is 1 point something, solution for y is this. Okay, so let me see if this is true. Okay, so I'll call this solution. Then let us try to print out the values of f x, the solution, SOL. So you expect that when this is pressed and f is evaluated at the solution, you should get the output for f1 and output for f2 to be very close to 0. To confirm this is true, let's check it. Yes, you always check it. So this is output for f1, output for f2. So yes, indeed. So the answer is that this is your solution. So your solution is SOL, and this is your x, and this is your y. Blah. So you solve the answer, right? So the answer for these questions, for this solution, is f is 1, and then y is this, right? fx is this. So okay, so what is actually the ex? Ex is just exponents of 1, so that means answer is just 1. Okay, exponents of 1. Yeah, I think this is a solution. So exp 1, and then this is the number of y. So what is the value of y? Y is this number. Okay, so if x is 1, that means we have to have a log of y give you e. Okay, so the log of y equals to e means that the log of y, the y has to be this number. Okay, so let's just try again. Let's print out the NP log of this number. Sorry, log of 15.15. So I'm trying to print out the numerical values of log of the solution, this one, and I expect to see a number which is e power 1. So yeah, so e power 1 is just the natural number. So we have checked, right? So I have shown you how to use the optimize function fsolve to solve a set of differential equation, a set of a simultaneous equation, and then after you have solved it, then you check it. So that is basically what is being done here. Now this is a slightly more complicated situations. You have another set of differential, another set of equations which is like this. We call this ellipse equation. So this is an ellipse, and this is also an ellipse. So this describes an ellipse. So you see, ellipse is the generalization of a circle. Now for those who have forgotten, a circle has a function of x squared plus y squared equals to r squared. So if the radius is different along the x directions and the y directions, then it becomes an ellipse. Like ellipse is a general case of the radius, where the radius along the x and y would not be exactly the same. Okay, so the general an ellipse has an equation that looks like this. I think in general, the ellipse has a general form that looks like this. Okay, so if a and b are the same, equals to r squared, then you get an equations of a circle, and x and h and k is the center of the circle. So if you draw a circle in the middle of 0, 0, that means h and k will be 0, 0, and then you set a equals to b equals to r. That will reduce it to a circle. But in general, the ellipse would have a center which is located not at the 0, 0, and the axis along the x and y direction would be different. Okay? So I think this is called semi-major, this is called semi-minor. A is called semi-major, B is called semi-minor. So this is an ellipse. So I think the ellipse has this form. Okay, so this is an ellipse. So the ellipse has x and y. Sorry, this is a center, and then there's another center. So we have two ellipses here. So I think this ellipse, this equation is this ellipse is an ellipse located at the center 0, 0, whereas this equations is another ellipse which is located at a h and k located at 0.5 and 0.25. So let's look at this. So this is 0, 0. So the blue color dot refers to the first ellipse, whereas this orange color ellipse is an ellipse that is described by this equation. Okay, so we have two ellipses. So what we want to find is that what are the intersects of the two ellipses. So you look at this ellipse here. This is a blue ellipse. This is the orange ellipse. So they have four intersections. This intersection, this intersection, this intersection, and this intersection. So there are a total of 4 intersections, and we want to find out what are the intersections. That is, what is the x coordinate, y coordinate at this point, x and y coordinate at this point, x and y coordinate at this point. Right. So this is again another example of solving the simultaneous equation. We want to find out what are the x and y. So there is a total of 4 solutions because there are 4 intersection points where these two ellipses meet. So how do you solve this? It's very simple. Again, you define one function for the first ellipse, you define another function for a second ellipse, then you just use fsolve to solve it. So maybe I don't do it explicitly, you just follow the code here. So again, you define f1, which is 2x squared plus y squared minus 1. Right? So this is what I do. 2x squared plus y squared minus 1. So here, the x here is an array that contains 2 components. The first component, I call it x0. Then this is a component, I call it x1. Okay, so this is very similar, exactly the same as this one. Like in this previous case, this x is an array that comprises of 2 components, x0 and x1. So there are many ways how you define this. So I define, well, I just call x an array, and then I just assume that x has 2 components. So that's how I define the first equations. Then this is the second equation, f2. f2 would be 0.5 x0 minus 0.5 squared plus 2 times, this is x1 minus 0.25 squared equals minus 1. So this is how I define my f2. Right? So 0.5 x. So the x here in the function f2 is the first, is a 0 component. It's a 0 component in the x. Okay. So after you have defined f1 and f2, then you define the function f, which is made up of function f1 and f2. So this function f again is a array that contains 2 functions, f1 and f2, and our purpose is to vary the array x such that the function to be minimized could be made to become 0. Okay, so you need to provide your initial guess, then you define your functions in the argument of fsolve. So fsolve admits 2 arguments: the function to be minimized, which has been defined here, and also the initial guess, which is a 2-dimensional array. So this number refers to the initial guess for x, and this number 1 refers to the initial guess of 1. So we want to know what is x and what is y. So if you finally find out what is the x and y in this simultaneous equation, it actually refers to the coordinates of the intersect. Right? So here you have 4. So say if you want to find out what is this intersect, you should provide an initial guess that is close to this point. So this point is somewhere between, well, maybe somewhere here, around minus 0.5 for the x, and then maybe 0.5 or 0.75. So you can try to locate this point by providing an initial guess that's close to this. So I'll take, for example, x to be minus 0.5 and 1 and y to be 0.75. So let me change my initial guess. So my initial guess is, what was it? 0.5 for the x and 0.75 for the y. So this is the initial guess that I would supply x 0.5 somewhere here, x 0.5 and 0.5. So I expect that when I put in this initial guess, I will be able to obtain the solution for this point. So let's see what it is. So I define this and print it. Yeah, so the solution is this and this. And indeed, I checked that when I place the solution into the function f1, f2, yes, I got a 0. Right, so that means it's also, that means the intersect is located at 0.48 and 0.72. So that solution refers to the intersect at this point. Okay, so this is the coordinate. Now, how about if you want to get the coordinate for this? So you have to supply an initial guess which is close to this. So it looks like minus 0.5 for the x and minus 0.25 for the initial guess for the y should be sufficient. So let me try this. If I change this initial guess from minus 0.5 and 0.25, right? So minus 0.5 minus 0.05. So minus 0.05. So this is the initial guess. Okay, so this is the initial guess. So this is the initial guess that should land me onto the intersect at this point. So what is the exact coordinate of this? So the answer could be obtained by just executing this. So this is the solution, minus 0.43 and 0.06. So I suppose this is then the coordinate for this point. Right. So this coordinate is close to minus 5 and is between minus 0.25 and 0.0. So this is a coordinate. I forgot what the coordinate is already just now. Sorry. I can't remember the number well. So this is the initial guess, and the solution for this initial guess is this number. So let me cut this and then place it downstairs. Okay. Okay. So I guess the initial value to be this number, and the exact number is minus 0.43. So this is minus 0.43, and then 0.065, 0.065, no, I think this is not quite true. See, this is not the intersection point for this. I'm looking for an intersection point of this, but what I get is the solution for 0.0625, 0.0625. So sometimes I think there's some problem here. I cannot identify the solutions. This is minus 0.43, so minus 43 is somewhere here, and then this is 0.06. 0.06 is very close to 0, so it looks like it is locating at this point, which is not the coordinate I'm looking for. So it looks like something is wrong. So I don't feel very comfortable with these solutions here. So let me try again. Okay, sorry. Solution. Okay, sorry, I'm right. I look at the wrong place. So this is not. Okay, this is the values of the functions at x init. So this is not 0 because the initial guess is not the solution. So what I should be looking at is the solution. Okay, the solution should be 0.7 and minus 0.121. Okay, so this should, yeah. So I guess I provide the initial guess and I land on the final solution, minus 0.7 and minus 0.12. So yes, I think this is the location, right? So this value is very close to, yeah, this value is minus 0.7 and minus 0.12 for the y coordinate. Okay, so if you want, for example, this, what should you do? The initial gas should be provided to be close to, say, 0.5 and 0.5. So let's just try this again. 0.5, this should be 0.5. Okay, so if I do like that, then it looks like the solution is this, right? So I provide minus 0.5 and 0.5. So if it's minus 0.5 and 0.5, then the solution is this, right? So this refers to what point? This refers to, I think, no, this refers to 0.55, so minus 0.48 minus 0.48 negative 0.72. Okay, I think this is the, oh, no, I think I looked at the wrong answer again. Okay, so the solution should be this 0.72 minus 0.5 minus 0.5. No, it should be 0.5, not minus 0.5. Should be like this, 0.5. So if 0.5, then the solution is this 0.5. Okay, sorry. Now I want to look for this. So the initial gas should be 0.5 and the y value should be minus 0.5. 0.5 minus 0.5. Yeah, so this should be like this. So the solution is minus 0.29, 0.29 and 0.99. Yeah, I think this is this point. Okay, so if you make the initial gas to be minus 0.5 and 5, minus 0.5 and 5. Okay. Now anyway, what I'm trying to show you is that you can try to do a different gas for your solutions, then you get a different answer. So if your initial gas is close to one solution, you get to that solution. So there are 4 solutions. So all these solutions could be obtained one by one by providing the initial gas. Okay. So I hope that you get the idea. Okay. So I just want to show to you that when you change your initial gas, then the solution you get will be close to that initial gas. Okay. So that is the exercise for this. Now, any questions before we take a break? Okay, so if there's no questions, we will take a break for 5 minutes. We'll come back at 4:11. Then we should be able to continue. Okay, at 4:11 we come back, we break for 5 minutes. Any questions, you just prepare it. Either you ask it or you post it in the chat. Okay, so we take a break now. Okay, for those who have not signed in attendance, you can take your attendance now. So while waiting, you can try to talk to me. Okay, anyone? Just talk to me through your mic. It's okay. Okay, no one talk to me. It's fine. Okay, so I hope that you are back there. So there are questions. There are assignments. Okay, so I have an assignment for you, which is like this. Okay, so a very short assignment. You will have it today. I'm going to upload it. A very simple assignment. So I think 1 question, 2 questions, 3 questions. Very simple. So the first question is just like, I just find it from some internet. You just have to solve this simultaneous equation, variable y and z. So try to find me what is the values of h of y and z to fulfill this set of simultaneous equations. So you should, this is a guess, right? You initial guess, you put this and see whether it works. And this is slightly more complicated. Now this is not been taught to you, right? So in the examples that we have discussed just now, you solve a set of 2 simultaneous equations. But in this case, you have 3 simultaneous equations, 3 variables x, y, and z. Then you just try to figure out how you would write your code to solve these 3 these 3 simultaneous equations. Now this is also not a very complicated graph, but it should be quite simple. So it's an equations where you have variable epsilon over d given to you, and then r is some constants. You have to write a code, a for loop or things like that, in order to find out what is the values of f. So you have to change the values of r from 10 to the power of 3. So you fix the values of r, then you solve it, find out what is the values of f. After you have found the values of f for one r, then you have to change the values of capital R again, so that you got different values of f. So after you have done that, then you have to plot the function of f, the values of f as a function of r on a log scale. So so if you do this correctly, I think the answer, I think I've already got the answer. I think this is the solutions. I5E, this is the solution. I'll just go through this very fast. Then this is the last one. So if you got it right, this is what you got. Okay. Now maybe your answer will be slightly different than mine, but anyway, this is the answer I got. So I expect that when you run this assignment, and you have to write a for loop to vary the values of r, then you have to plot the function of f in different values of r that are ranged from this power 3 to power 5. And when you got it done, then they should be like this. So this is the values of log of r. You are not plotting f as a function of r, but log of r. And you figure out how to do this. Okay, so this will be the assignment later today. So it should be quite simple. Okay, so let us try to finish our today's lecture. So we have solved the functions, this matrix equation, just straightforwardly. But now I just want to add some additional exercise, right? So let's just try to plot this. How are you going to plot the coordinates of these two ellipses? How? So in order to plot an ellipse functions, you have to refer to the parametric equation. Now you should understand what you mean by parametric equations. The parametric equation is a set of equations that describes the locus of some curve. So for example, this is a collection of coordinates for one curve, and sometimes we call this the locus, right? So you can describe a pair of parametric equation. If you describe the pair of parametric equation correctly, then you'll be able to generate this ellipse. And you have to also find out what is the equations, the parametric equation that describe this ellipse. So you have to be able to know how to convert an elliptic equations into a parametric equation. So this is what I'm going to explain to you. Let's just look at this equation. This is an ellipse. Now, ellipse in general has this form. This is the general elliptic equations. Elliptic equations is basically described by three different quantities. First is described by the semi-major, that is the axis of the ellipse along the x directions, and also the semi-minor, which is the axis of the ellipse along the y directions, and also the location where the ellipse is located, like the center x and y. So the center is located at the coordinate of h and y. So coordinate h, y is the location. So for example, here is 0, 0. So this is a 0, means that h and k for this ellipse is 0. So the ellipse has a semi-major. No, sorry, I think semi-major is this, okay? And then it's a semi-minor. So I just call, I think for ellipse, the longer axis you call it semi-major. The shorter one you call it semi-minor. So for this large orange, the semi-major is lying along the x direction, and the semi-minor is lying along the y direction. Whereas for this, the semi-major is lying along the y direction, and the semi-minor is lying along the x directions. So the center for this is hk 0, 0, and the center for this hk is somewhere here. Okay, so an ellipse that is given by these equations has a radius of a and b, and has a coordinate of the center h and k. So you have to figure out what is the coordinate for the center for this ellipse, and what is the semi-major and semi-minor. It's going to be very simple, right? So you just have to cast these equations, number one. So let's look at this ellipse. Just have to cast this equation into this form. Then you'll be able to tell. So just do some simple rearrangement, this ellipse equation, when you cast it into the form of x minus h squared divided by x a squared plus y minus k squared b squared, then you get into this form. Right? So this is a form that is like this. Then you just have to compare. Right? So for example, the number that goes into the denominator a squared is half. So that means for these parametric equations, the values of a is just square root of 1 over square root of 2. Right? So a squared is half. Therefore, the a is just 1 over square root of half. Whereas the b for this ellipse is just 1. Okay? Then you can do also similarly, this parametric equation, this ellipse, just try to cast it into this form. Right? So you just cast these equations into this form. It's very simple, right? So just pull out a factor. This is x over 2. Then this is minus 1 over 2. Then you just pull out a factor. Then you can easily convert these equations algebraically into this form. Right? Once you have converted into this form, then you can compare this form with an equation here. So a squared is your 4. So that means the a for this parametric curve is just 2. Whereas here is your half. Half is your b squared. So that means again the b is 1 over square root of 2. And this is your h and this is your k. So for every parametric curve like this one, the corresponding a is this. Well, this a squared, b squared. And then the corresponding h and k is 0, 0. Now once you understand that, then the parametric equations for the ellipse is just expressed and parameterized in terms of this formula. X equals to a cos theta plus h, y equals to b sin theta plus k. So you just cast this ellipse into a set of two parametric equations. One describes the coordinate of x, the other one describes the coordinate of y in terms of what we call the parameter theta. So you introduce a parameter theta. When theta change from 0 to 2 pi, then the values of x and y will be generated. Right? So this x at a certain theta and y at the same theta would define a point on the xy plane. So when you vary the theta, then the x and y will vary accordingly. If you collect all the values of the parameter x and y for all values of theta between 0 to 2 pi, then what you get is a shape of an ellipse. So what I'm saying is that the parametric equation that is highlighted on the screen describes the ellipse. So you just have to find out what is the a and what is the h for that equations. So here we have already explained to you for these equations, the a is this is obtained from here, and then is the b. So the set of parametric equation corresponds to this ellipse according to the prescription I just explained. Is given by the set of equation y equals to sin theta and x equals to cos theta over 2. So this is just a special case of this type. So you have to find out what is the value of a and b and values of h and k for the parametric equation. Now for this ellipse, once you cast this into this form, then you can easily identify the a for the x coordinate in the parametric equations is 2, and this is h. And for the y coordinate, the b is 1 over square root of 2. Then this is the values of the k, right? So you just follow these prescriptions, then you'll be able to work out. So now, what I have done is that I have successfully created these parametric equations and also these parametric equations. So these parametric equations will describe this ellipse, and then these parametric equations describes this ellipse. Okay, so let me try to do this. I think we still have some time. I'm going to generate the first ellipse and then generate the second ellipse. Okay, so what we need to do is that just define these functions, and then we will run it and generate on the plot. Okay, so just an example, define the x coordinate. Well, since this is the first ellipse, call it x1. So x1 would introduce will emit a parameter theta, and then the x1 is described by this function, right? So for the first ellipse, the x is cos theta over square root of 2. So I'll say this x is equals to return cos np cos theta divided by square root of 2. So this is 2, square root is raised to the power of 0.5, right? So this means square root of 2. So that is how I define my x coordinate in terms of parameter theta for the first ellipse. And then for the y coordinate in the ellipse number 1, the function is just sine theta. It's just sine theta. So this is just sine theta without anything. So it's just sine theta, and the rho is 1. So then I have this coordinate. So now what I'm going to do is that let me define the theta. So theta is to be defined as an variable that is going to change from 0 to 2 pi, and we're going to generate many theta points, say 1 degree, 2 degree, 3 degree, 4 degree, 5 degree, up to n degree. So how many theta point of theta you want? So just say, okay, let's say np arrange. So arrange starting from 0 and with 2 pi. Okay, np dot pi 2 times n pi. Now when I use n pi, I better import numpy as np. Okay, so that would give me n values of theta starting from 0 up to 2 pi, and then it's going to vary at some delta theta. Now the delta theta is the intervals or the resolutions of the angle. Now what is the angle I wanted to do? What the delta theta I want? So I usually define my delta theta in terms of the last values of theta minus the first values of theta divided by n intervals. And how many intervals I want? I just specify it in my code. So the last value is n, 2 times pi. So this is the last value, which is just 2 pi. So I divide the 2 pi into how many intervals? N intervals. I call it nt. Now this n intervals is usually a fixed number, say maybe 10, maybe 25. Okay, 25. So I'm going to separate the angles from 0 to 280 degrees into 25 sections, right? So then this will be the theta. So let me see what's the theta. So this is theta, right? It starts from 0 and it ends to 2 pi, right? But it doesn't end to 2 pi exactly, because this is not really 2 pi. So to make it to end exactly at 2 pi, I have to make it to be plus this, right? Then it ends up with 2 pi. Okay, so this is the last values of 2 pi. Okay, so once I've done that, then I'm almost ready to generate the coordinate. Remember, I want to plot the parametric plot, right? The plot for the first parametric curve is to provide the values of the x coordinate and the y coordinate for the parametric curve x1 and y1. So I should have x1 and y1, right? So this x1 and y1 has to be values. So I have to generate this. So how am I going to generate this? So I call this for say theta. Call this theta. But since I already used the theta here, I better use some other name. I think maybe I don't call this theta. I just call it theta ARR. Okay. So this is an array. So I'm going to make theta. Okay. So before I do that, let me do this. So I'm going to generate x1 that runs for theta in this. Now what do you get this? I'm going to generate a list of the values of x1 evaluated at theta, where theta is in the range of the theta, right? So if I were to do that, I'll generate into an array. So this is a one-liner, what we call a one-liner code that would generate the array of x1 for theta evaluated at this. So let's see what I get. Right? So this is the values of x1 at different theta. Right? x1 at theta, I think 0. This is x1 at theta equals to delta theta. This is x1 at 2 delta theta. And then the last one is x1, the coordinate of x1 evaluated at 2 pi. Okay, so that is how I generate my x theta, my x coordinate. And then if I want to generate my y coordinate, that is what I do, right? So this will generate my x coordinate and y coordinate. So now, what is this? This is two array that describe the x coordinate and y coordinate for the parametric curve. So so I just call this. So I just call it parametric curve 1. It would be a collections of this. Then I just plot this, right? So okay, so I put this into an array. Then I just say plot. I'm not sure whether this will get me the correct answer. So this PRMT is an array that comprises of the x coordinate and y coordinate of the parametric curve. And in order to plot, I have to import pilot from pilot import everything, right? Did I get anything? Yeah, it looks like I get something to execute 2 times. Yeah, no, this is not right. Okay, something is not right, so it doesn't work because maybe I just, yeah, so it looks like this is just not what I expect, right? So maybe this is not correct. So let me try this again. So this is x coordinate and y coordinate. Maybe I just put it like that. Yeah. So this is a correct. So it should not be enclosed in another array. So I just call it parametric curve 1, which is defined to be like this. And then I just plot this. No, it doesn't work like that. I still have to put this in this form. Okay, only then it works. Okay, so this is a parametric curve, and if I were to plot it, I might as well put it into a dot point so that I can see it more clearer. So I put it into a dot form, then this is how it looks like. Okay, so this is a parametric curve that has the coordinate at the center h and k, right? So the h and k for this coordinate is just 0, 0. So let me try to plot the center as well. So how do you plot the center of h and k? So I also plot the center, which is the h and k, which is 1, which is 0 and 0. So the h and k I define to be here 0 and 1. So I'm going to plot hk. Whether it works, I'm not sure. But I think it should work. Plot. No. So the plot should be a point like this. Yeah. No. I think it's not quite right. H and K should be just like this, I suppose. Yeah. No. 0, 0. Should be 0, not 1. It should be 0, 0. Okay, so that's how I put the center of this point into here. So maybe I'll just write this as this. Okay, then for this plot, I'll, instead of having a dot, maybe I should increase the resolution to be, say, 50. then you can see the point to be closer, right? So maybe not dot, maybe a continuous line. Right. So this is the plot for the first coordinate, for the first parametric plot. Now, if you do the same thing, then you can do the same thing for x2. Right. So this is the x2, and then this is y2. So I have to define my parametric equations for the coordinate of x2 and y2. Right. So just do it here. So for the second parametric curve, it is x2 and y2, and I have to be very careful about the formula. So the coordinate for x2 is 2 cos theta plus 1. Okay, so let me write it here. 2 cos theta plus 1. So x2 is 2 cos theta plus 1. The 1 is h. Well, the 1 is h1. Okay, I'll call this h1. Sorry, h2, because it's referred to the center for the second parameter. The center coordinate x for the second parametric curve. Then the y coordinate is this, okay, where the k is 1 over 4, and this is this 1 over square root 2 sine theta. Okay, so this is this has to be multiplied with 1 over, well, 1 over square root of 2. 1 over square root of 2 should be like this as 1 over 2 with a square root of 0.5. So this is square root of 2. So this is 1 over square root of 2. And then plus 1 over 4. Plus 1 over 4. Now 1 over 4 is the K2. So I call this K2 to be 1 over 4. And then I'll call this H2 to be 1 only. Right? So this is 1. Refer to this number. Okay, so now I have my H2 and K2 defined for Y2. So the H2 K2, well, the H2 K2 is just this. Okay, so I'm going to plot the H2 K2. So when I plot the program, this should give me this now. Okay, so I'm going to off this for the moment so that I can only print out the second coordinate, the second parametric curve, which was this one, which is different than this one. So let's see if it works. Yeah, so this is the coordinate. Maybe I'll call this a different point, which is say, don't know what I use, maybe a plus, okay, and maybe just like this, so that it looks different. Maybe this is maybe like this. Yeah, so this is a second coordinate, and this is a second parametric curve, and then I'm going to make both to be merged together. Okay, so by opening up this one and this one, if you don't say anything, you will merge all the plots in a single figure. Okay, let's do this. Now you see this, right? So you have the center and the center, right? So you have two coordinates, and then this is the intersect, this is intersect, this is the intersect. So it will be very simple, right? If you know how to translate the parametric curve from these ellipse equations into the parametric curve, then you should be able to plot these functions. Okay, to plot the locus of the ellipse. So imagine this. Okay, maybe in some test later on, I'll give you some arbitrary ellipse that looks totally different from this one, but still an ellipse. If I ask you to convert into the parametric equations for the ellipse, which is this general form, you should be able to do it. So then you have to extract the corresponding values of A and B, H and K. And if you have already obtained the parametric equations, then you'll be able to generate the coordinates for the parametric curve using these things, okay, using the techniques that I have shown you here. So basically this is what we are doing here. So it's slightly different than what I do. This is the code that I originally coded yesterday night, but during this moment I'm now doing a slightly different way to generate the plot using this method, which is slightly different than this one. So you can generate the coordinates for x and y using this method, or that method isn't the method. So finally you get this. Okay, so we have to conclude today, we learn how to find the intersections between two parametric plots of two ellipses, and then the solutions to the intersection depends on how you provide the initial guess. So in this case, you provide different initial guess, you got different intersection. So now I give you a simple exercise. Maybe I should do this in the assignment that I'm going to put up after this lecture. Do you think it is possible for you to modify the code that is being developed here? Right. So this, for example, only find you the solution for one intersect. Now how about if I want you to do this? That is to modify the code so that you can automatically obtain all intersections. Therefore, can automatically locate this, then extract the coordinate of these 4 intersections, and then plot it onto the orbits. So for example, here you have only one intersection marked. So I want you to modify the code so that when I press the button of your assignment, your code should not only return me these 2 ellipses, but also should mark the intersect of these 4 points automatically. Okay, so that is what I'm going to do with you, but you have to figure out how. Okay, so this is your exercise. It should not be very difficult, but you have to think. You may have to write a for loop code, or you have to do some smart programming. Okay, so that is the assignment I want to give it to you today. So maybe later on. Okay, so I have not uploaded the assignment yet to the EE module, but maybe expect it today. Okay, I give another week this time because of we have online lecture, we don't have face-to-face meeting, so I give you 1 week, 7 days to submit the assignment. You are always free to ask me anytime, any questions. You message me, you discuss it in the WhatsApp group or whatever. So I'm always be prepared to handle any questions. Okay. So I'm still continuing to prepare the lecture notes for the next few lectures. So it is still an ongoing process. So you see me uploading the new lecture materials, lecture notes from time to time, and you always will see that this lecture material will be constantly undergoing changes. Okay, so I think we are not going to make the course very difficult. I'm going to give you some very simple numerical tasks and show you how to do the simple programming using Python. And after we have equipped with all the necessary knowledge of using the Python syntax, then only we will go to the physics part. Maybe we will look at some dynamics process that you learn in your first year or second year, say the pendulum, trajectory, and maybe collisions 1D and 2D. So we try to use Python code to simulate the processes. So that is what you expect. So in the first part of the course, as I mentioned during the face-to-face session before the lockdown, the plan is to divide the Python script, the Python class into 2 sections. The initial part is to learn the syntax by going through some simple exercises, solving numerical equations. And then the second part is to use that syntax that you learn from Python to simulate physics. Okay, so that is more on application, but the first part is more on the learning of the syntax. We have not finished with this part yet. We are going to spend 1 or 2 more weeks on the applications, well, not application, the syntax, say integrations, and maybe doing some statistics. Okay, the simulation of the physics will be done maybe much more later. So I think it's a very lengthy code, a lengthy class, so I'm not going to bore you with that. If there's any question, you can ask now. If not, then we're going to finish it, finish the part of the lecture today now. Any question? I'm waiting for any of your response before we end this meeting. No? Sure. You have no problem. Okay. So I hope that you are enjoying yourself at your home. Take care of yourself and don't get yourself infected with the virus. Okay. So if there's no question, then we end our meeting here for this today. So thanks for your attendance. Okay. Okay. I'm now meeting here.